Someone was telling me that thinks he's taking 2 PE classes this term, so he's, I think, running kind of ragged, trying to get back and forth between that and his regular classes. All right, we are now recording, and let's go to current slide. This is where we left off last time, I think. I believe that's coming on. While we're waiting for that to come up, I don't know if any of you are interested. I think one of you may be, so this is be for you. Have y'all ever heard of the Noyce Scholarships? It's a program sponsored by the National Science Foundation. And this one is Alabama A&M has launched a AAMU Noyce Scholarship. You know about it?
I've heard about it.
Okay. I know UAB had one and Tuscaloosa had one. They're only like 3 to 5 year grants or something, so theirs may have expired. I don't know. But we've had students participate in it before, and they have thoroughly enjoyed it. Okay? Now, I don't know how AAMU, Alabama A&M is doing theirs, but what the others have typically been, I think universally, they're trying to encourage people from a variety of majors into getting interested in teaching mathematics or sciences. Okay, so y'all are prime targets for them. And whether you choose to do that or not, but I know one of you is thinking of it, it would be a great program. Okay, now, I don't know how A&M has set up theirs, but Brian's here. How the others did, it varied from 3 weeks to, I think, most of the summer, like, 9 or 10 weeks, and so it may vary, but it's usually in the summer. They usually pay you a stipend to go and learn all this stuff. They provide room and board, I think, usually. It may vary. They provide transportation money to get there and back once, there and once back. Any other trips you make are on your own. And it's a great program. I mean, they give you lots of opportunity to see math and science and practice in classrooms and tutoring and just all sorts of things. And it is a summer program, but may not be the entire summer. I've had students before who, when they're on the 3-week type deal, still take a course, but those 3 weeks just follow on YouTube's and then come back and finish up the course. So you may be able to do part of a schedule anyway if you are going to plan to be here in the summer. But it's a great program. So if you're at all interested in it, check your emails, because this was sent to you just like it was sent to me.
And that's in Huntsville?
Yeah, A&M is in Huntsville, or I think actually the town is Normal, isn't it? Normal, Alabama, which is real close to Huntsville. I don't know exactly where, but somewhere real close to Huntsville. So check it out. It should be a good possibility. I know you may have work or family obligations or something that may preclude it, but check it out. It's really a good possibility. Okay, just wanted to get that said before we got going today. Next, are there any questions on anything we've done so far? All right. We're in 8.7. Chapter 8 is integration techniques and improper integrals. We're going to skip the improper integrals part because they're not very proper anyway. And we were on 8.7, integration by tables and other integration techniques. And we were down to the bottom of page 566. And we were just looking at, note that the integrals in Appendix B, which is in the back of your book here, and I wish I could give you a page number, but the page number is A3. Okay, they start the appendices off with the A's, and this is A3, so it doesn't tell you anything about a page number. And it's right before the answers. Now, this is a fairly limited table. It's only A3, 4, and 5, I believe. No, 6. A3 through A6, 4 pages. 100 integral forms that you can do. Now it says, note that in the Appendix B, they're classified according to the form of the integrand. And several of these forms are listed. U to the n, okay? That's a power form, okay? And those are equations 1 and 2. That's about it, okay? The rest of them are pretty easy to do from there. Then an A plus BU forms, okay? Now the A plus BU forms are 3 through 13, okay? And then the A plus BU plus CU squared, those are 14 and 15, okay? And so you go on like that. Square root of A plus BU as opposed to A plus BU, those are the next few, and then A plus or minus U, A squared plus or minus U squared. The square root of U squared plus or minus A squared. Square root of A squared plus minus U squared. And then the trig functions, inverse trig functions, exponential functions, and logarithmic functions. And that pretty much wraps up all 100 of those that are in the back. Okay? So, let's do some. I think the first one is example 1. Find the integral of dx over x times x minus 1. All right. Now, if you go back here, that would be, doesn't look like any of these, except closest would be this one, I would think. So let's take a look back there and see if that will give us anything close to dx over x times x minus 1. Okay? Just looking at the others to make sure I don't see anything else that is possible. And they didn't mention here the hyperbolic functions and inverse hyperbolic functions. I generally don't focus too much on them at all. I'm sure there's plenty of applications for them, but so far in my life I've not run into many. So I'm not going to spend a lot of time on those, but they didn't even mention them on the previous slide, so we'll do. So, forms involving the square root of a plus bu. Well, in our case, a will be a negative number. Okay? And number 17 looks like it's the closest to what we need. You see that? That would be the integral of du over u times the square root of a plus bu. Okay? So, I'll keep everything in line here. All right. So, from the back, we know the integral, number 17, let me get my pen set up. Now, if you don't have a book, that's going to be sort of hard to follow, but I'll write down as much as I can. In the back of your book, and basically in any table of integrals you'll find something very similar to this, okay? From the back of the book, the integral of 1 over u times the square root of a plus bu. Now, if you need to, rewrite this as the integral of 1 over x times the square root of minus 1 plus x. Okay, now that looks a lot more like that, right? Okay. Now, what does this integral tell us it is? Well, this is a piecewise defined function. Okay. It's either 1 over the square root of a. Okay. Hold the presses. If you look at this, your x here, your a here is minus 1. To relate these two together, you can't use this one because that top one, because you can't do the square root of a. Now maybe if you use complex numbers, okay? We haven't done that, and I don't think that intent was there. But remember, this is a piecewise defined function. And notice the bottom. The top half was for a greater than 0. Hey, our a is -1. So we don't use this one, okay? The bottom one is when a is less than 0. Hey, we can use that. This will be 2 over the square root of minus a, which in our case is the square root of 1, which is just 1, okay? Arctangent, I prefer inverse tangent, but I'm going to write it the way they do, of the square root of a plus bu. Well, our b here, by the way, is also 1. B is also 1. So it's -1 plus x. In fact, the same thing we had before, okay? Over a -1. Your a. Oh, minus a, which is over 1, okay? So we could have left that off, plus c, okay? So what does this come up being? 2 times the inverse tangent of the square root of x minus 1, okay? All right. Oh, what did I leave off? Plus c, okay. Now, you didn't have to write it in that order, but that just seemed like the more convenient way to do it. Let's see what they got in the book. 2 times arctangent, I put inverse tangent, it's easier to write, square root of x plus 1 plus c. Perfect. Okay? Now, do I want to go back there and figure out how they got that? Not particularly. I'll just take it out of the table and run with it. Okay? All right. No objection to that? Okay, good.
Where can we find this stuff if we don't have the book like for the test?
Okay. I think I mentioned to you last time, wish I'd have thought to brought it up today, CRC tables, or find any old calculus book anywhere, library or somewhere else, you're going to find a list, an appendix or a table of integrals somewhere in it. And they will have most of those basic forms you just saw. I can't think of any of those tables that are fewer than 100 or so. This one had, before the hyperbolics, it was up to 93 or 94, something like that. A lot of them don't do hyperbolics, but this one threw those in at the end to get up to 100. The CRC, it has hundreds of integrals in the form. So just find the source, and they're basically all over the place. I don't know if there is I'm certain there is, I just can't tell you what it is, that there's a website that would just have table after table after table of integrals. I bet. All right, let's see how they did it. I think you'll see it's very similar to what we did. All right, to erase? Okay. Because the expression inside the radical is linear, you should consider forms involving the square root of a plus bu. Now, understanding then your a is going to be a -1 and your b is going to be a +1. Well, in the back of the book, sure enough, formula 17, when a is less than 0, which it is, because a was -1, then you had this form here. And of course, if a is -1, the negative a is 1, so that goes here and here. So that gives you 2 as the coefficient, arctangent of just square root of a plus bu. Well, what was the a plus bu? It was square root of x minus 1. So you could go back and write it same way we did. A is -1, b is 1, and u was x. Okay? Then du is dx, and you can write that same thing in this form, the 2 times the inverse tangent of square root of x minus 1. Exactly what your argument was under there. And that's what we got. All right, they're skipping to Lou their darlings. Number 2, example 2. So let's us do 2. Find this, the integral of x times the square root of x to the fourth minus 9 dx. All right. Now, what I'm going to do, probably unfairly, but just to do it, since they listed them out here, what would be closest to that one? Square root of x to the fourth minus 9. Okay? Looks like this might be it, doesn't it? So let's start with that as our key here, and all right. Go to the back of the book, the square root of u squared minus a squared. That's the one we chose, wasn't it? Yeah, a squared minus u squared. Okay. That was not on the first page. It's on the second page, A4, the bottom part of the page. And it could be forms involving u squared minus a squared. That looks better than a squared minus u squared. Okay? Because you'd have to turn it around then. So let's go with the square root of u squared plus or minus a squared. Okay? And start going through this. Okay. Understanding now that u is equal to x squared, and that makes u squared equal x to the fourth. Your a was 3, making 9 a squared is equal to 9, right? And we're going to go with the minus sign. Okay. Now, la-di-da. We need it with the, if u was x squared, we would need a root u in front. And frankly, none of these really look all that promising, do they? Okay. Well, let's look at the ones up above. And they look even worse. Okay. So did we go to the right placing? Oh, there's another. A squared minus u squared. Well, that wasn't quite what we have. None of these are really looking all that promising. Okay. They suggest that we try 26, which is the first one in the grouping that we were looking at, but it doesn't look exactly like this. Okay? But at least let's consider it. Okay? Now, again, let me make sure I've copied my program right. I think I have. X. Yeah. Okay. So our u is x squared. So u squared is x to the fourth. And then our a was 3, so a squared is equal to 9. And that's what we have, x to the fourth minus 9. Okay. Now, let's look at this a moment longer. If u is equal to x squared, then du is equal to what? 2x dx. We need that in there. Well, there's an x dx in here, so we're really not all that far off, are we? Okay, it's just that we have to deal with the 2. Well, we can divide out the 2 and make this du over 2 is equal to that. Okay, so let's see what we've got now. We've got the integral of 1/2 x dx would then be du. Oh, let me not write it there. Sorry. Yuck. Okay. Okay. And then we would have the square root of u squared minus a squared, because a squared is indeed 9. Okay, and then you would have the u, because we took that out front. We have exactly that form now. So we can basically write down our answer. Got to put the 1/2 in front, and that will be a u times the square root of u squared plus a squared. Now here's what I do with this. Since that's exactly the form that you have inside the integral, leave it in that form. Don't put the plus or minus in there. Leave it in exactly that form. Times the square root of u squared minus a squared. We'll come back and plug in a minute. Okay? And then it says plus or minus. Well, we have a minus, because we got a minus there. A squared times the log. Natural log, absolute value, u plus exactly what's in the radical, square root of u squared minus a squared, not in the radical, in the integral, square root of u squared minus a squared. Okay? Absolute value. Block that off, plus c. Now let's plug in what our values are. Okay, 1/2, and here's Daniel. You're right, he is still alive. Okay. Clarky said he saw you around today. So we knew you were around. All right, your answer, your u was x squared. Okay. The square root of u squared minus a squared is simply the square root of x to the 4th minus 9. Okay? Minus a squared, which is 9, times the natural log of, your u was x squared, plus, and this is the same radical we have, u squared minus a squared is x squared minus 9. Square root x squared minus 9 plus c. All right, that's our guess at the answer. Let's see how we did. Where did the 1/4 come from? Oh, I left it off. That's where it came from. Oh, I'm sorry. I had a 1/2 in there. When I wrote down mine, I forgot that I already had one. This was from the back of the book that had a 1/2 in it. We had a 1/2 in front of that, so that makes it 1/4. Okay, sorry about that. 1/4 x squared times the square root of x squared minus 9 times the log of x squared plus the square root of x fourth. That's 4th, minus 9, close parentheses, plus c. Except for a few exponents here and there and a fraction denominator here and there. It's the same answer, okay, isn't it? All right. Makes sense? Okay. Now we're on page 567 in section 8.7, integration by tables and other integration techniques. We just finished example 2. And by the way, example 2, you can see larsoncalculus.com for an interactive version of that type of an example. So you can go there whether you have a book, whether you have a code, or anything else. And by the way, let me think. Have any of you used the code I gave before? Have you looked it up or anything else? The reason I asked this is I gave them all 7 courses I'm teaching using their product. And one of the first ones that I got any feedback from was from Math 113. They said these examples are from intermediate algebra. I said, what? So they had done a 113 course but used a Math 100, which I'm not even teaching this term in that. Well, I taught it last term, and what he did, he just copied the one he did last term. Well, last term they did it wrong, okay? But no one in the class even used it to let me know they had done it wrong, so they just copied it over. So they're trying to get that straightened out. That's why I wanted to know if any of you have looked up to use their code, and if you have, if everything looked copacetic with it, if it seemed okay. If not, I'll get them to go look at that. But if y'all aren't using it, it doesn't matter to me. I don't use it either. But it does have good tutorial help and additional problems. Maybe related to those in the book. They make it sound like they are related to those in the book. All right, everybody got this one? Can I move to the next? Okay, this is example 3, bottom of page 567. Integrate this one. This time, it's a definite integral. Well, you can do definite integrals too. You just won't have a plus c. This will be the definite integral from 0 to 2 of x over 1 minus e to the minus x squared dx.
1 plus e.
What's that? Oh, that's 1 plus, but a minus x squared. You're right. Okay. Now, frankly to me, that looks like it's just ready to use substitution anyway. I don't think you'd have to go to a table to do it. Okay? Let u equal either x squared or minus x squared, and then du would be either 2x dx or minus 2x dx. It doesn't matter whichever way you choose to do it. And then you got your x dx there, put a 1/2 out front, and then you have a du over 1 plus e to the u. And then you can do that. That may be how you wind up doing it, because that one I don't think is integrable. Okay? So what you might want to do, let's see what they say. Yep, they say exactly that. This, don't go looking in the back of the book for one like this. Get it into a simpler form, so to speak, that we can't integrate and then do. So exactly like I said, first thing is let, and let's see, which way did they say? Yeah, they said let u equal, include the minus sign, minus x squared. You don't have to, okay? It'll work without it, but I'm going to do it the same way they do. Then du is equal to minus 2x dx. We don't have a minus 2x dx, we just have x dx, so let's divide both sides by minus 2. Okay, so they go out here, stay in there. So this will be a minus 1/2, the integral from, I'm going to leave off the units for now. Du is x dx, or negative 1/2 du. I already got negative 1/2 out there. So du would just be then left x dx. So we have an x dx, so this will just be a du over 1 plus e to the u. That's the one that we can't do, okay? I can't think of any way to do that one that's reasonable. So what we do is look up that in the table. And if you flip back a page, you'll notice it says just exponential functions. So we need to go back there and find our exponential functions. All right. Forms involving not the exponential functions on the last page, A6, and this is just above the middle of the page, 81 through 86. Integrals involving e to the u. Excuse me. And this certainly is an e to the u. And number 84 looks just like this. I mean, precisely like this. Okay? And oh, wait. Time out. I forgot my limits. Okay? You could proceed, go back and then resubstitute in and then evaluate, but let's just see if we can do this. What is u when x, see, on this integral here, these are values for your variable x. When x equals 0, what is u? Or what are you? 0, okay. So that will be the same. Okay, and when x is 2, 2 squared is 4. And then negate that, a minus 4. So that one up there is going to be a negative 4. Ew. I don't like having the smaller number on top. So what can we do about that? Change the sign. Well, there was a minus 1/2 in front. That leaves a 1/2, the integral from 0 to 4 of du over 1 plus e to the u. Now we'll proceed. Okay? Like I said, that's exactly number 84. So we'll write down what the answer is. The answer is 1/2. That's from our integral. And then we have a u minus log of 1 plus e to the u. Oh, wait a minute. They didn't put absolute value bars following that log, did they? Is that an error on their part?
No, because of the e.
E to the u is never negative. Ever negative. Not even 0, ever. And add 1 to a positive number, you get a positive number. So yeah, you don't need the absolute value bars there. Okay, I didn't finish writing. Oh, yes, I did. I left off the plus c because this is a definite integral. We'll evaluate that from 0 to 4. Okay, so let's do that. It's 1/2. We'll leave that out front. And we'll plug in 4 for u because that's what those limits are there for. Therefore, oh, I did them backwards. Y'all let me get away with that? What's wrong with you folks? We're going from minus 4 to 0. You swap the values, but you don't change the values. You don't negate the values. That's the opposite. In other words, the minus of minus 4 to 0. Okay. So we're going first. So let's get that set up too. All right, I'll start by plugging in 0. Okay, that would be 0 minus the log of, and you evaluate that for me. Oh, you don't need a calculator.
I was getting my calculator out for the next part.
What's that?
I was getting my calculator out for the next part.
For the next part, okay. And he expects me to believe it. Okay, now, what is e to the 0?
1.
1. Anything to the 0 power is 1. So that would be, and 1 plus 1 is? 2. You didn't know you'd be doing such high-level math today. So that's log of 2 minus log 2. Okay. Then we do minus the same thing evaluated at 4. Well, when I'm going to put it in parentheses so we hopefully minimize our chances of making sign errors. That will be a minus 4 minus the log of 1 plus e to the minus 4. Right? All right. So this will be a 1/2 minus log 2 minus, I'm going to change that since both of these are minuses. Let's just make everything a plus. Plus 4 plus log 1 plus e to the minus 4. And that should be our answer. You can plug in the numbers if you want to. Another thing you could do here is write this as log of 1/2. It would be 2 to the minus 1, which is 1/2. If you wanted to do that, that would be a fairly negative number. Just like the log of 2 is a positive number, and negate that, it would be a fairly negative number. And then 4 plus blah, 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 blah. E to the minus 4 is a really, really small number, not far off from 0. So you got 1 point something another, not super all that close to 0. And then you take log of that, and you'll have something just beyond 0 that you have to.
I think I got it.
Okay.
3.325.
Let's see how they did. Uh-oh. Let me see if I did it right.
Oh, I didn't do 1/2.
Oh, that should do it for you then. Just take that answer divided by 2.
Yeah, there we go.
Huh?
That was it.
Yeah, you get 1.66. Yes. Okay. They even show you the graph of that, which I was not about to do, and you're determining the area under that graph. All right, good deal. Now, that being done, any questions on how to use the tables? Also, you'll find in your tables reduction formulas. They don't give you the answer, but they give you how to get the answers. And these are called reduction formulas. Usually things that are fairly high power, and then you do a reduction and a reduction until you get down to something you can do, which may be looking up at a different part of the table. But that's what we're doing here. So several of the integrals in the integration tables have the form integral of f of x dx is equal to sub g of x plus some new integral h of x dx. Such integrals are called reduction formulas because they reduce the given integral to the sum of a function and a simpler integral. Okay? And at some point, you should be able to do that last integral. Even if that's by another place in the table, you should still be able to do it. So we keep reducing the degree of those, of your answer. Goodness gracious. Again, I rushed through lunch and didn't drink enough fluids, and now I'm just about dried out. Okay, so let's do this. An example 4. Evidently, the PowerPoints they provided in their My Resource area were have not been upgraded. Evidently, 4 and 5 were added. The ones that we just, no, I'm sorry, I'm looking at the wrong page. It's right there. It's here. Find the integral of x cubed sine x dx. Yuck. Okay. Now, my guess in the table, this will be of a form like this. The integral of u to the n sine u du. I'm guessing that's what it'll be in the table. Let's go back here and look and see what it is. Okay? These involve your trig functions, sine and cosine. So these look to be, ones between 46 and 58. So let's see what we can do. Ha! 54 looks just like my proposal here. Integral of u to the n sine u du. All right. So let's note here. Yeah. Oh, did you have something?
I just wanted to ask you. I'm looking at the right thing here. Mine says, mine is x to the n, but it's sine h. X
In the book?
Oh, sir, it's on my
Oh.
I don't have it in my book. I don't have those pages.
Oh, okay. So this is from a different table somewhere.
See, it says
Okay. X to the n. No, that's not it. Which is it?
x to
Oh,
the
no. Okay, that's hyperbolic sign. That's not the right ones. Okay. It's this one. X to the n sine x.
Oh, yeah, I see it.
That one. Okay. Hyperbolic signs are the ones we're probably not going to do. I'll introduce you to them if you need them, but, you know.
So like anytime, like the cosine h is cosine, it's like...
No, it's a different function.
Hyperbolic?
Hyperbolic cosine. Has really nothing to do with cosines. It's just the derivatives and the integrals look somewhat like sines and cosines, which to me, leave them alone. Don't even confuse it with sines and cosines. The functions, if you graph them, they don't look a thing like sines and cosines. So why? Well, because the derivatives are, and some of the rules for them are similar. Like you have the Pythagorean theorems for sine squareds and cosine squareds. For hyperbolic sines and cosines, you have Pythagorean-like identities, but they're not the same. So to have them similar but not quite the same is almost worse, because then you're so likely to use the same one, but you forgot, oh, no, this one you change the sign. This one, Actually, what a hyperbolic sine and cosine can just be written in terms of e to the x and e to the minus x. And those are, to me, so much easier to work with, taking derivatives of and integrating, than are the hyperbolic sines and cosines that you have to remember new formulas for. So I tend to avoid those if I can. Some areas you may really need them, so stand by for that. So like I say, this was our number 54. Okay, and our number 54 says that the integral of u to the n sine u, now remember n for our problem is equal to 3 and u is equal to x. I'll write that down too. X equal u. U equal x, u or x, okay, whatever. Okay, then this, the answer to this would then be, I'm just going to write it right out of the book, if I can keep my eyes on it. There it is. Minus u to the n cosine u plus n times the integral of u to the n minus 1 cosine u du. Now, I don't know if you recognize what they're doing here. It's just integration by parts. Okay? You're letting u equals, it's hard to use u. Okay? You went back and let that be x cubed. Okay. Then let let's go back and do that. U equal x cubed. No, wrong. Yeah, I think it's right. U equal x cubed, and du is equal to sine x dx. Okay? Then derivative of x cubed, that would be derivative of the first one would be, no, this doesn't work out that way, does it? Thought it did, but it doesn't. I guess they're letting no, it does. I think it is. Okay. But since they've already given it to us, let's not reinvent the wheel. Let's just use it. Okay. So what is this then in our plan? That's a minus x cubed cosine x, x is u, plus 3 times the integral x squared, u is x, and n is 3, so n minus 1 would be 2, cosine x dx. Okay. All right. Well, I still can't do that second integral. But number 55 is very much like that. Okay. Where n is now 2 and u is x. Okay. So what we'll have, I'm going to bring it over here. Bring out that first one, minus x cubed cosine x plus 3 times, and this integral here will be x squared sine u okay, sine u sine x. Goodness gracious. I'm feeling almost dizzy here. Minus. See, the other was a plus. This is a minus because of the sign problems you have here. And it's in, oh, and by the way, I should have put this. For this one, n is equal to 2. Okay? And x is equal to u. Okay? U is equal to x, whatever. Okay, so that will be a 2 times the integral of, and again it's the n minus 1, so it'd be x times cosine, cosine x dx. Okay? Now, it's sine, I'm sorry, I meant to write sine and I wrote cosine. I was looking above. You're right. Good catch. Okay. I was just going to say go to number 52, which has that integral in it. And now we have, and this will just be everything following that. From 52, that would be sine u minus u cosine u plus c. All right. Final answer is minus x cubed cosine x plus 3x squared sine x minus 2 sine u for some reason, okay, almost getting lost here. Okay, plus 2 sine u minus 2 sine u plus 2, not u, x. Goodness gracious, I keep forgetting. Okay, plus 2x cosine x plus c. Whew. Okay, I think that's done. Okay, now notice patterns here. Your x exponents 3, 2, 1, 1, 0. Flip order there. Okay. Your signs, minus, plus, plus, minus. But when you think about derivatives of sines and cosines, that's how they go. Minus, plus, plus, minus, plus, like that. So go like that. And your trig functions are cosine, sine, cosine, sine. So they're alternating every time. And then you have a plus c. At least that looks fairly reasonable. Let's see how it compares to what they got in the text. Minus x squared cosine x plus 3x, no, minus x cubed cosine x plus 3x squared sine x. Oh man, here's what I forgot. These have a bracket on it too, so it's 3 times 2. This will be a 6, and that will be a 6. Okay, the c doesn't have to be in that, but the other does. Okay, sorry about that. I forgot to bracket everything in there. So plus, I didn't write mine in the same order, minus 6 sine x plus 6x cosine x plus c. Yeah, sorry, I forgot to bracket in, get the 3 outside, because that was outside the entire integral. And I forgot to do that. Okay, so there's a reduction formula. Each time you use it, reduces that exponent by 1. You keep going until you get one that doesn't have an integral anymore, and then you're through. All right, example, oh wait, that was example 4. Let's watch them do it then. And if you like any of their approaches better than mine, fine, go with it, okay? Consider the 3 formulas listed below. Now this is, you wouldn't consider these unless you'd already worked the problem and found out you needed them. So this is a little disingenuous to start with that one, which definitely is not any of those, okay? And then this one, yes, that is that one. Okay, so that's where on I would start with. Consider this, where the x is u, the n is 3. Okay, that would be sine x dx. That would be perfect. That's minus u to the 3, x to the third, cosine x plus 3 times the integral of this one. Well, that's formula 54. We're going to need formula 55, which is this one. So then this one, which was a 3 times the integral here, this will now be, rather than n minus 1, that's what it was there, meaning 2. Now we're going to use that as your n here, 2. So the integral of x squared cosine x dx, which is exactly what that turned out to be, is, and remember, the n, that 3 goes in front of all this, but we don't use it, don't need it yet, x to the x squared sine x minus 2 times the integral of x, 2 minus 1 is 1, so x sine x dx. That's this one right here, okay? So, in computer programming, you call this nesting your loops. And so that's what we're sort of doing here. We're nesting. You got to remember there's a 3 on the outside of that one, the 2 on the outside of that one. And that's what this one is, okay? So now we go to this. The integral of that is minus x cubed cosine x plus 3 times the integral of that one. And that one turned out being, oh, they carried that all down. 3 times x squared sine x minus 2, inside the parentheses there, 2 times the integral of that. This is where I left off my parentheses. Okay. This one plus 3 times this one minus 2 times what's, no, 3 times 2, which is 6, times this one, and that was x cosine x minus, actually a sine x minus x cosine x plus c. All that nesting, you have to remember those constants out front, which I didn't. Okay. Now, they're obviously skipping one. That's not a lot of room to write there. Let's see if, whoops, That's more room to write, so let's do it here. This is example 5. Find the integral of the square root of 3 minus 5x over 2x dx. Now, it was at this point I was going to turn it over to y'all and let y'all find them, but none of you have a book readily available here. So I guess I'll go through it again. But I don't need the practice in this as much as y'all do. Wish I would do it. So here we have a square root of 3 minus 5x. Well, that looks like something we had back at the beginning. So let's go back to the first page. This is page A3. And that form of square root of a plus bu. That's what we've got here. Okay? So we have a form like the square root of a plus bu. Okay. Now this is in the numerator, whereas the 2x is in the denominator. Ha! Number 19 on page A4 looks like the best fit for this one. So let me list what equation 19 is. The square root of a plus bu over u du. All right. Not a perfect fit by any means, but something. All right. Now, in order to make this work, it looks like to me, in the simplest form, u has to be 2x, doesn't it? Okay. So let's say that. Let's start with there. Let u equal 2x, or let u equal 2x. Okay? I guess while we're there, then let's just say then du is equal to 2 dx. Okay, so you got to remember that. Okay? Now, if u is equal to 2x, but what we have in here is a minus 5x, okay, then that means that b is equal to minus 5x, but that would be a minus, now this takes some effort here. Let's maybe do this. That means u over 2 is equal to x, right? Going that way. So this will be minus 5 u over 2. I think that's right. Okay. If b is equal to minus 5x, which it is, then and x is equal to u over 2, then b would equal to minus 5u. Wait, that's not right. bx. No, I'm sorry. b would be minus 5. Sorry. b would be minus 5. But what form we have here is minus 5x, and minus 5x would be okay. b is minus, okay. Hang off this a minute. Okay, let's go back to what I had. bx is equal to minus 5x, okay? And x is equal to u over 2, so bx is equal to minus 5 u over 2. So that means the bx bx is minus 5 over 2u. Okay. Now, what is your a? Your a is 3. Okay, I think we got all the pieces in place now. Okay. Let's write down what this is. That's number, what do I say, 19? Yeah. It's equal to 2 times the square root of, and it's your a plus bu. Well, your a plus bu from here is exactly this, so just write that down. 3 minus 5x. You don't have to go back and forth so many times. A plus bu is 3 minus 5x. Okay? Plus a was 3. And now we have another integral here. Yeah. 1 over u, and our u is 2x, times derivative of a plus bu, square root of a plus bu is exactly our 3 minus 5x. Okay? And then our du, I know it's here somewhere, du is 2x. So this will be, let's bring the 2 out here and make it 6 dx. Okay, I think I missaid it, but I wrote it right. All right. Now, but we can take this out and make it 3 again, okay, because the 2x down in the denominator makes it a 3 there. Okay. But now we've got an integral like that, which now you have that in the denominator, and that looks a lot like number 17. Okay? And number 17, again, is just like we did before, only, we used it before, I believe, only this time the x is u, not what we had before, and the a plus bu will be, a will be 3, and this time the b will be the minus 5. We don't have that fractional form anymore. Okay? Okay. So let me see if I can get this written down before I lose my mind here. The a this time is still 3. So this time we're going to use the upper one here because a is positive. And the b, the b will be minus 5. So a is equal to 3 and b is equal to minus 5. And u is equal to x. So everything should be fine here. So let's see what our answer is. 2 times the square root of 3 minus 5x plus 3, and the integral of this thing would be the upper one here, 1 over the square root of 3 times the log, absolute value, and that numerator is a plus bu. That's exactly what our 3 minus the square root of 3 minus 5x, okay, minus the square root of 3 over the square root of 3 minus 5x plus the square root of 3. That's all in the absolute value sign plus c. Okay. Now, this can be written as 2 times the integral of 3 minus 5x plus, square root of 3 will go into 3, the square root of 3 times. So root 3 times the log of the square root of 3 minus 5x minus root 3 over the square root of 3 minus 5x plus root 3 plus c. Okay. I'm glad we're through it. I hope we're done with that one. Let's go back and see how close we were to what they have in the text. Goodness, I'm getting dizzy with that one. Now, why do they divide by 2? Except for a factor of 2, I'm there. Did I have a 1 over 2 somewhere here? Yes, right there. Right there. This du is equal to 2 dx. So dx was 1/2. There's where I forgot. This has a 1/2 in front of it. Sorry about that. Sorry, I just lost the thing. Okay, so that would wipe out that 2 and put this over 2. Sorry about that. Okay, had a 1/2 in front of all that. Okay. Always something. Okay, but you get root 3, wherever it is here, root 3 minus 5x plus root 3 over 2 times the log of root 3 minus 5x minus root 3 over root 3 minus 5x plus root 3 plus c. Oh, man. All right. That was example 5. So let's move on to...
Maybe too.
I'm sorry?
I mean, it's maybe too broad of a question, but how do people figure out all these square roots? And I mean, who came up with all these?
Okay. Believe it or not, most of these probably could have been done using the techniques we had. They've just written the results here. Now that one, I don't recognize as being close to anything we did. The others, like that one I think right before that was a integration by parts and integration by parts and integration by parts. I don't know how many of them. And that would have given you those. And that would have been perfectly fine. You could have done that, but they just condensed them. This one, I can't recognize anything that would come out exactly that way. And here's Catherine. We finally break the, get an X chromosome in here. It makes things look a lot better. Okay, good deal. And it's 5 people here, 5 people there. It's good. All right. So now we're moving on to rational functions of sine and cosine. Okay, rational functions meaning ratios of sines and cosines. But they're functions of sines and cosines. They're ratios of functions of sines and cosines. And here's the first one of these. This is your example 6. The integral of sine 2x over 2 plus cosine x dx. Okay. I feel like a sneeze coming up. Sorry. Should wake everybody up at home. Okay. Now, we're doing integration using tables, and there's a small table in the back of your book, but if you have other tables that work better, use those. Clark found one on his phone that does pretty well. All right. These are forms involving sines and sine u and cosine u. There's 46 through 58. Let's see if any of these come anywhere close. A problem here is that you have two different u's here. And they don't have any of those in the back. So I think what you have to do here is go back to your trig, and by the way, that's in the front of the book, I think, and let's figure out what sine of 2x is. Anyone remember? Ring a bell? Sine of 2x is 2 times the sine of x cosine x. If not, you want me to take it one step further back to see where that came from? Or are you happy with that? You want to go back another step? Huh? You what? You're okay with that. Okay, that's what it is. So let's try that and see. So that will now be the integral of, I'm going to take this 2 on the outside and try not to forget it this time. Sine x cosine x over 2 plus cosine x dx. Now let's see if that's any closer to anything in the back. Afraid not. Okay. Yuck. Okay. Now, if not, here's something you might try. Don't know if this is going to work for you, but let's give it a shot anyway. Multiply that denominator by its conjugate. I know that would work if it's a 1. With it being a 2 there, I'm really doubtful. 2 minus cosine x. If you do that, you also have to multiply the numerator by 2 minus cosine x. And then we have our dx here. Okay? Well, that denominator becomes 4 minus cosine squared x. Which doesn't look a lot better, does it? Okay? And you might say that's 3 plus 1 minus cosine squared x. And 1 minus cosine squared x would be sine squared x. So now you've exchanged it for a 3 plus sine squared x in the denominator. I don't think that gets you any better. So this must not be the route we should take. Okay? All right. Okay. We started off well. That last step didn't help us at all. So we're going to undo that completely. Okay. Thought there might be a little bit of benefit in looking at that. There wasn't. Okay. But here's what they say do now. Since this is a linear form down here, let's let this be 2 plus u. So let u equal cosine x. Sound okay? So let's see. Let u equal cosine x. Then du is equal to what? Anybody? Negative sine x dx. Well, there we have a sine x dx already up there. And we have a u up there. So this may actually be working okay. So what do we have now? We have 2 times the integral. Let's put the minus out there with it. Minus 2. And the sine x dx is du. And the cosine x is u. and this is over 2 plus u. That looks like something that maybe we can work with from a plus bu. A u over a plus bu. Oh, look at that. That's number 3, isn't it? Where your a is 2 and your b is 1. So let's do that one. It'd be the integral of u du over a plus bu, right? It's exactly 1 over b squared times bu minus a log a plus bu, jump down, sorry, a plus bu, which, yeah, a plus bu. I think I wrote it right. Okay? Now, to get from here to there, our a is equal to 2, and our b is equal to 1. So this will be a minus 2. Don't forget the minus 2 here. And this will be 1 over b squared, which is 1 over 1 squared, which is 1 over 1. So leave that out completely. Bu is just u minus a, 2, times the log of 2 plus u plus c. But remember, we got to go back and plug in what u is, or u are. So this will be a minus 2 times u is cosine x minus 2 times the log of 2 plus cosine x plus c. Okay? And then multiply the minus 2 through, you get minus 2 cosine x plus 4 times the log of 2 plus cosine x plus c. Now, if you don't like leading off with the minus, switch the order and make it 4 log, blah, 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 blah. Okay. Let's see how they did. Minus 2x plus 4 log 2 plus cosine x in absolute value plus c. Yes. Now, let me make a contention to you. Don't you think we could lose the absolute value bars here? Because cosine x stays between minus 1 to plus 1. So even when this is at its least, that's minus 1 plus 2. Yeah, we could put parentheses there. We don't have to have absolute value bars. Okay? Never did it look like it was going to come out that way. A fairly simple seeming answer for something that was a fairly complicated looking article. Thank you very much. All right. That's how we did it. Let's see how they did. Can I erase? All right. They first start off with, you can't have two different arguments. One a trig of 2x, the other a trig sine of x. So let's use our double angle formula to do that. 2 came out front just like we took it out front. Sine x cosine x over 2 plus cosine x. That's not in the table under your sines and cosines. Anywhere under the sines and cosines. Anywhere close to anything under there. So then the deal was, well, that looks like a plus b u. So let's do it that way. So that doesn't apply to any of the listings there for sines and cosine. So let's consider the a plus bu, where u is now going to be cosine x, or actually bu is cosine x. Okay. and that's the formula. Don't start with a formula, okay? Let's start with the substitution, okay? And the A would be 2, right? The B would be 1, and the U would be cosine x. Yeah. Then you're going to need a du of minus sine x dx. So you pull the minus on the outside and make that a, they do this so strangely. The minus comes out here, and this will become a u du over 2 plus u. And they're going back to the other slide and doing all the things there with this, and that's the same thing we did, but this is so disjointed here, you have to flip back and forth between the two. That's why I wouldn't have written that down until we got to this place here, so it would be closer. That's exactly what we got. Yep, exactly like we got. All right, any questions? So we got the same answer they did. All right, now rational functions, substitution for rational functions for sine and cosine. This is what we were just doing on the last two examples. For integrals involving rational functions sine and cosine, the substitution of u is equal to sine x over 1 plus cosine x is the same as tangent of x over 2. Ha! You are asking where that one came from. Here's where it comes from, right here. This actually comes from another trig function, Trig's identity. I'm going to try to find it for you quickly, but none of you have a book anyway. Do you, Catherine? You got an e-book? Or not? Okay. If you ever do find your book, or a book, on the front inside cover, it's a sort of a cardstock cover. The back side of that, here are some of your trig identities, okay? And this one right here, there is a tangent, okay. I thought it was right here. I'm not seeing it now. I thought so. I'm looking for the half angle thing for tangent, and I think they just don't have it in here. They have the double angle, but I don't see their half angle formulas here, which is a shame. They ought to be here. Yeah. Man. Okay. And I would say, let's see, I don't think they're going to be anywhere in here, but let me just look another place or two. See, on your back page like that, they have algebra on one side and geometry on the other side. So let's see if I can find half-angle formulas in the index. I'm thinking not, because they didn't have them where they belong. Half-life, no half-angle formulas. Sorry about that. If you still have an algebra book, pre-calculus algebra, something like that, go to your half-angle formula for tangent, and you'll find 3 different forms. This is one of the forms, okay? So if you do have rational functions of sine and cosine, if you get it down to a linear-like form like this, that is another way to do the half-angle of tangent, okay? Now, if you then solve this, let's see, yeah, then you do what I was suggesting before. Do multiply and divide by 1 minus what can I think of the word now? Conjugate. Multiply by the conjugate of the denominator, and you have a 1 minus, multiply by 1 minus cosine x. No, maybe that's not the best thing to do yet. But it takes a little bit of work, and you can get to cosine x being this, sine x being that. And why in the world wouldn't they be using dx up there? But they didn't. They did it down here. Wow. How you get from here to there is you write x over 2 to be 2 times the inverse tangent of u, and then the inverse tangent of u would be is that. So, man, they go all sorts of weird ways to get there. But these are some other substitutions you can make, only if necessary, okay? Look them up if you need them, okay? Let's see if they do any more. All right. No, they just say you can use them. That finishes 8.7. Homework exercises number 3 is both at calcchat.com and also at calcview.com. 5 is only at calcchat. You can do either 7 or 9. They're both at calcchat. 11 is at calcchat. 13 is at calcchat. You could do either 15 or 17 or both. They're both at calcchat. 15 is at calcview. You could do any of the odds 19 to 39. They're all at calcchat. Then do any of the odds 41 to 47. They're all at calcchat. 41's at calcview. Any of the odds 49 to 53. They're all at calcchat. Yeah, none of them are at calcview. Any of the odds 55 to 61. They're all at calcchat. You could do 63. It's at calcchat. You can explore doing 65 if you'd like. It should be at calcchat. 67 is a work problem. That should be at calcchat. 69 is a population problem. That should be at calcchat. 71 is a volume problem, and that should be at calcchat as well. All right, we're not going to do improper integrals, so we're through with Chapter 8. Let me give you the test for Chapter 8. Okay? If I can lay my grubbies on it quickly here. Now, don't be offended, okay? This says Cal 2 at the top. This is Cal 3, okay? But this was a test covering Chapter 8 in Cal 2 that I did on summer. And everybody started off a lot further ahead than we did. So, you can see that we got Jordan. Okay, you won't take that. All right, and who's the other one we're missing?
Vince.
Yeah, Vince.
What's his name?
Vince. Vince.
Vince, got it. Any of you see Vince? Any of you other classes?
I think he has you in leader algebra.
He
Yes,
does.
sir. I think.
That will be tomorrow, yeah.
Yeah, I think.
Yeah. Okay. So I will do that. Did that run us out of time?
Yes, sir.
Oh, too bad. That's so sad to hear. All right. Then I'm going to cut down, and we will go from there. And next time, okay, let's talk about this too. We're not going to do Chapter 9 Infinite Series because I don't think anything in the subsequent chapters are going to need that. If you wanted to look at it, 9.1 and 9.2, actually into 9.3, if you got anything to look at, I never do any more than those in it. We're not going to do 9. We need to move on to whatever's next, if I can get to it. This is one long chapter. Okay, 10, conics, parametric equation, and polar coordinates. Let me think on this a moment. I think let's start with 10.2. Oh, it's not going to hurt us to do 10.1, 10.1, 10.2, and 10.3 maybe. I don't think we need polar coordinates. So that's what we'll go to next, 10.1, 10.2, and 10.3. We'll try to move fairly quickly through those because 11 then is going to build on the parametric equations especially. And 12, and the end of 11 we'll use the conics. All right.
Well, yeah, have a good one.
You too.